All right, let's learn a little something about parallel circuits. Before we do that, however, we should probably review the rules for series circuits to make sure that we fully understand these so that we can contrast them with the rules that we're going to develop for parallel circuits. So if we look at the series circuit here off to the right, we can see we have 3 resistors in series with a battery. The simplest rule is the rule for resistance, which states that the equivalent resistance of a circuit is equal to the sum of the individual resistors. That makes sense when you think about a circuit from the perspective of an obstacle course. The electrons have to go through all 3 obstacles in sequence, therefore it makes sense that you would have to add up their difficulty values or their resistances. The potential difference rule states that the potential difference at the battery, which is a gain, must equal the sum of the potential differences at the individual resistors, which happen to be voltage losses. This rule stems from Kirchhoff's second law, which states that the gains in potential in a closed loop in a circuit must equal the losses. So if we put a meter in to measure the potential difference gain at the battery, that must be equal to the loss at resistor 1 plus the loss at resistor 2 plus the potential loss at resistor 3. The simplest rule is that for current, which states that the total current measured near the battery must equal the currents measured near each of the circuit elements. This is quite simply because when current leaves the battery, let's measure it with an ammeter, and we'll call it I total. When current leaves the battery, if you think of the mental model of current being like water flowing in a pipe, you're not going to lose any of this current, so it just continues to flow because there are no branches in the circuit. So if you measure the current over near resistor 1, we'll call that I1, it should be equal to the current measured over near resistor 2, I2, which should be equal to the current measured somewhere over near resistor 3. Incidentally, it doesn't matter if you place the meters before or after the resistor, it will still measure the same current value. This rule helps with the idea, which is one of the big misconceptions in circuits, is that current doesn't get used up. Potential difference gets used up as you head around the circuit because the gain at the battery must equal the losses at the individual resistors, but the current does not get used up. It stays constant throughout. Remember, this doesn't mean that you can't change the current in a series circuit. It just means wherever you measure the current, it will always be the same in a given circuit. Let's take a look at parallel circuits. Let's develop the rules. The simplest rule, I believe, is the potential difference rule. Here we have 3 resistors connected in parallel to a source of potential difference, which happens to be a battery. The hallmark of a parallel circuit is that current will have a choice. When the current leaves the battery, it can choose to head through one of the resistors, or it can continue straight and head out to the others. This junction is what helps to make the circuit a parallel circuit. The easiest rule is the potential difference rule. If you note that the positive terminal of the battery, if you trace the wires, seems to be connected directly to each of the resistor's legs. The battery itself is touching resistor 1, resistor 2, and resistor 3. On the other side of the battery, you can see that it is also in contact with the other leg of resistor 1, and resistor 2, and resistor 3. So from the perspective of these resistors, they all feel like they're wired directly to the battery because indeed they really are. That leads us to the rule for potential difference, which says that the potential difference of the battery must be equal to the potential difference across resistor 1, which is equal to the potential difference across resistor 2, which is equal to the potential difference across resistor 3. As for the current, as I was previously explaining, if we measure the current leaving the battery, which we will call I total, that current will then head around, and when it encounters its first junction or node, Kirchhoff's first law takes over, and the sum of the currents entering the junction must equal the sum of the currents leaving the junction. So some of the electrons will take a left turn and head up through resistor 1. The rest will continue straight. At the next junction, some of the current will choose to take a left turn and head up through resistor 2, and the remainder of the current heads around and goes through resistor 3. One of the key elements is after passing each of the circuit elements, all of the current meets back up on the top and joins together. So if we were to measure the current up on the top branch, we would also be measuring the total current once again up there. It's because current doesn't get used up in a circuit. The total current simply split, went through the resistors, and then joined back together. So these two total current readings should be the same. If we insert meters in the branches, we would call this one I1, which would measure the current passing through resistor 1. And we'll call this current I2, and we'll call the current on the outside loop I3. If you picture current branching and joining back up, it should help you with the rule that the total current is equal to the sum of the individual currents. I2 plus I3 plus dot dot dot. The potential difference rule, if you recall, was that the battery potential difference V total is equal to V1, is equal to V2, is equal to V3, is equal to dot dot dot. As many resistors as you want to put in parallel. The bizarre rule, which takes some getting used to, is the equivalent resistance rule. In series, when you add more resistors, it leads to a higher equivalent resistance because we add them up. In parallel, when you add additional resistors, it lowers the resistance of the circuit, which is very bizarre behavior indeed, and it definitely requires some explanation. The equation that allows this bizarre behavior to happen is 1 over the equivalent resistance is equal to 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3 plus dot dot dot. As many resistors as you'd like to do it with. So let's take a look at calculating equivalent resistance on the next slide. So here we have 3 resistors placed in parallel. It doesn't matter what the battery potential difference is. The resistance of resistors is an inherent property of the matter, and they do not need to be connected to a battery to have resistance. So, as a good physics student, let's write down our equation. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. Let's substitute with units. 1 over the equivalent resistance. Notice that the left side doesn't say Req, it says 1 over Req. That plays a big role in finishing solving out this problem. Equals 1 over 25 ohms plus 1 over 50 ohms plus 1 over 100 ohms. Now, we'll use our calculator in a moment to do the example the second way, but let's first use our math skills and find a least common denominator for the right-hand side, which would obviously be 100. So we can rewrite this as 1 over the equivalent resistance will be 4 over 100 plus 2 over 100 plus 1 over 100. Therefore, 1 over the equivalent resistance is 7 over 100. In order to get our answer, we would have to invert both sides or simply flip them over. So the equivalent resistance will be 100 divided by 7, which will be 14.3 ohms. Now, it's important to be able to do it by finding a least common denominator, but let's talk about how to use your calculator. The button you'll use a lot in this unit is the inverse button, the x to the negative 1 button, which is the button immediately below the math button on your TI. The expression that you would do on your calculator, 1 over Req would be 25 inverse plus 50 inverse plus 100 inverse. When you do that on your calculator, you would get, as before, 1 over REQ equals 0.07. To find the final answer, we need to flip or invert, and you will once again get an equivalent resistance of 14.3 ohms. It is really important to remember to flip, because if you just calculate the right-hand side and report that as your answer, like the 0.07, you know that's going to be an answer on a multiple choice question. You need to flip it over. A couple of handy rules of thumb. If you put multiple resistors in parallel, like a 15 and a 7, the equivalent resistance will always be less than the smallest resistor. So in this case, it would be less than 7 ohms. That is always true no matter how many resistors you put in parallel. The equivalent resistance will always be smaller than the smallest resistor. A more handy resistor rule, and it's convenient for standardized testing because in many standardized tests it's convenient to write questions that have identical resistor values. When you put identical resistors in parallel, the equivalent resistance will be, if you take the value of one of the resistors and divide by the number of resistors, you will get the equivalent resistance. For example, if you have two 4 ohm resistors in parallel, take the value of one of them, 4 ohms, and divide by the number of resistors, and that gives us our 2 ohms as advertised on the right. Similarly, if you take two 6 ohm resistors, you will get a 3, and two 12 ohm resistors, you will get a 6. This also works with any number of resistors. The example on the right has 4 10 kilo ohm resistors. So the way we would solve this out, you would take one of the resistors, which is 10 kilo ohms, and you would divide by the number of resistors placed in parallel, and we would get a number of 2.5, which if we do our reveal on the meter, there it is, 2.5 kilo ohms. It's also important to note that there are many ways to draw a parallel circuit. I typically do it the way it was depicted in the previous examples, and that's typically the way you'll see it on a standardized test. But it is also possible to draw circuits in other ways. So when the electrons leave the battery here, this is our negative current that we're following. The current will head down and eventually encounter a junction here, and then the current will have to split and go through the resistors. So whenever there's a junction and the current splits, then we're going to have a parallel type arrangement. It could be series parallel combination, but in this particular example, it's just straight parallel. So be on the lookout for circuits that are drawn slightly differently, but if you follow the path of the electrons, they're essentially in parallel. All right, that brings us to a complete example. We have a circuit drawn off to the right. It is simply 3 resistors placed in parallel with a battery. And the knowns for the problem are over here on the left, highlighted in blue. Resistor 1 is 13 ohms. Resistor 2 is 1 ohm. And resistor 3 is 6 ohms. So let's begin by finding whatever we can find next to help us fill in the remainder of the unknowns. I think the easiest thing to do is to note that the battery potential difference is 12 volts. That's our V total. And if you look at your New York State reference table on the electricity page, off on the right-hand side, it has the 3 rules for parallel circuits written there for your reference. If you look, it states that the potential difference across the battery, 12 volts, is equal to all the other potential differences. So I'm going to write 12 volts, 12 volts, 12 volts. The next thing we should probably find is the equivalent resistance of the circuit. Here we have a 13, a 1, and a 6 ohm resistor all in parallel. So 1 over the equivalent resistance will be 1 over 13 ohms plus 1 over 1 ohm plus 1 over 6 ohms. When you run it through your calculator, you will hit 13 x to the negative 1 plus 1 x to the negative 1 plus 6 x to the negative 1. When you get your answer, you will hit the inverse key again, and your calculator will display answer inverse, and you will get an equivalent resistance of 0.804 ohms. Please note that the 0.804 is indeed smaller than the smallest resistor, which is 1 ohm. So we will write 0.804 ohms for our equivalent resistance. Let's work on the currents. It should also be noted that you can use Ohm's law wherever you would like to employ it in a series or a parallel circuit. You may remember that you need to keep the subscripts together. For example, V1 equals I1R1, V2 equals I2R2, and so on. So here, in order to find the total current, we can employ Ohm's law because we know V total and we know R total, so we should be able to solve for I total. I total will be V total over the equivalent resistance. When you do the 12 volts divided by 0.804 ohms, you will get 14.92 amps. That's a lot of current. That is the total current leaving the battery, which if we put in a meter, we would install it right there to measure the 14.92 amps. It's still the total current because the current has not encountered its first branch yet. We would also do I1 is V1 over R1. If we do that, we will get 0.92 amps for current 1. We will get 12 amps for current 2. And we will get 2 amps for current 3. Please note that the individual currents add up to the total current, even though we didn't force them to. It's the way the math worked out. I would like to draw your attention to the amount of current that went down each branch. You can see the largest current by far took the second branch. You might be wondering, why didn't it take the first branch? The first branch is so much closer. Well, it turns out the first branch has the highest resistance, so very little current will want to go down the first branch. You may have heard the expression, current takes the path of least resistance. That's why the 0.92 amps heads down the first branch. The second branch draws most of the current because it has the smallest resistance at 1 ohm. So current is indeed taking the path of least resistance. And the 2 ohms heads down the 6 ohm branch because that current is kind of in, that resistance is kind of in the middle somewhere. The powers, we can employ our power equations much like we employed Ohm's law. We can do P total is I total V total, P1 equals I1 V1, and so on, to multiply out the powers. If we do that, we will get a P1 of 179.04 watts. Power 1 will be 11.04 watts. P2 will be 144 watts. And P3 will work out to be 24 watts. You can work the math yourself to prove to yourself that you can find the individual powers. Notice that the individual powers add up to the total power. So that's how parallel circuits work. Hope you enjoyed the video.